Nanopores are used in scientific instruments to identify molecules, like DNA. Here's how it works. You pass your molecule through a tiny hole, the nanopore. And as it passes through the hole, it generates electrical signals. And those electrical signals form a unique fingerprint that lets you identify the molecule. There's been an explosion of interest recently in nanopores. Here are just 3 examples of companies just to highlight interest in the field. But all of these companies are building static nanopores, which just means that the hole is fixed in size. What that means is they can't look at things that don't fit in the hole. So practically speaking, most of them can only look at DNA molecules. We've taken this technology to the next level. We invented mechanical nanopores, which means we can change their size. Because of that, one instrument is going to be able to look at all kinds of molecules.
This is a prototype Demonpore. There's a light from the bottom, and what you see is an atomically sharp blade moving back and forth with nanometer precision. We call this method sliding occlusion. The motion is controlled by piezoelectric nanopositioners, which are cheap and easy to manufacture. The sensors in your phone use them. And here you see how current is proportional to the cross-sectional area of the pore. The yellow line moves up as the pore opens and down as it closes. Like with nanopositioners, electrical amplifiers have been miniaturized for the memory in your phones and computers. We can do this very quickly. Here we're doing it several times a second, but we've done it hundreds of times a second with consistent results. And here we're using another atomically sharp blade to open and close a circular Demonpore. In this case, where the pore is too small to see, it's in the center of the dark circle, and we're still able to detect the state of the pore as we move the blade back and forth. So what do we actually use Demonpores for? The utility of a pore is to detect things as they pass through. Here you're seeing a cloud of blood cells approaching and then flooding through a Demonpore. The spikes in current correspond to transit events of cells as they pass through the pore, and these spikes contain rich information about individual cells. By partially closing a pore, we can slow the cells down and get more precise information on them. But not only can we slow them down, we can also grab and hold them for as long as we like, which we call capture and release. Cells are micron scale, but we've also demonstrated the utility of Demonpores at the nanometer scale. Here we're grabbing and releasing individual nanoparticles repeatedly with precise control. We call this the nanoparticle turnstile. Traditional static nanopores get clogged and become unusable very quickly. It severely limits their device lifetime. And in contrast, we've shown that Demonpores can be regenerated, which drastically increases device lifetime. So, what does the future hold for Demonpores? Well, a single portable device, something you can hold in your hand and plug into your phone, will have arrays of thousands to millions of individually activated Demonpores that can be reprogrammed on the fly with software for different applications. For example, you could use them for blood tests, you could look at food and water quality, you could test soil, you could size nanoparticles, test fertility, detect pathogens and toxins, and maybe most importantly, you can help biomedical researchers tease out the complex molecular mechanisms of disease.
And we are Demonpore. We built the world's first mechanical nanopores. It's a big step on the road to a holy grail of biotechnology, a universal biomolecular sensor. Thank you.